All right, so just a couple things when we start doing our regular stoichiometry. One thing that's really important is the molar mass. You definitely want to remember the molar mass. It's used as a conversion factor, so remember it's how many grams there are in 1 mole of something. And again, we use it a lot in stoichiometry because it can be used as something to convert. So let me just see if this likes me. So just remember, like if we did something, there we go, like sodium hydroxide. If we were looking at the sodium hydroxide molar mass, you would just look up sodium, and that's 23.0 grams per mole. You would look up oxygen, which is 16.0 grams per mole. And again, these are just from the periodic table. And hydrogen is 1 gram per mole. So what you would do for the whole molar mass is add it all up, and it would give you sodium hydroxide, which is exactly 40.0 grams per mole. And then you can use this as a conversion factor in a lot of different problems that we have. One other thing to think about with Stoich is that when you do a stoichiometry problem, what you're doing is you're trying to make a prediction on something. And to make a prediction, you have to start with a balanced chemical equation so that you're making your prediction off of the thing that's really going to happen. So just remember, you have to have a balanced chemical equation. And again, most of the time, Stoich is used for knowing what's going to happen in lab. Or in business or whatever. If you're making a product, you want to know how much you're making or how much of the reactant you need. When you do stoichiometry, what you get as your answer is a theoretical number. So that's like if every single bit of reactant converts completely over to products. And that would be like ideal conditions, so like perfect world. When you do a lab, that's not ideal conditions. So you're never going to really get 100%. So, but what the stoichiometry problem does is it shows you the maximum amount of product that you could get in a lab. You should never get more than that maximum amount. Excuse me, because what that means is that you just created matter, which is not really possible. So you hope you don't get more than 100%, but you also hope you don't get significantly less than 100% as well, because that means that something's not right with your different abilities here. So what we're going to look at is just different problems dealing with some stoichiometry developed. So this is a graphic organizer. It helps certain people when they're doing Stoich problems. And what we're going to do is we're going to do like one of each type. And there's other ones you can practice as on your own. If you like stoichiometry, use it. It's a good organizer. If it doesn't help you, if you kind of see Stoich in a different way, then, just don't use it for you. But what you have is you have two sides of stoichiometry. You have your known side and your unknown side. And this is all written on. But what you do is you find out what the problem is giving you first. So is it giving you mass? Is it giving you particles? Is it giving you volume? Or is it giving you moles? And then what stoichiometry does is it shows you the process to get to the other side. So the first type of problem we're going to do is called moles to mass. So what that means is that they're going to give us an amount of moles, and you can see it's all circled up here. And then what we're going to do is we want to go to mass. So you can see that when we start here, we're going to have to immediately do a mole ratio right away. And then what we also have to do is we're going to have to go get the molar mass of our unknown on the periodic table. Excuse me, I'm just coughing. To do this. So when we do these problems, it's going to be two conversion factors, and we need the mole ratio, and we need the molar mass. So here's one problem of it right here. So what we're doing is photosynthesis. So you can see here we have the chemical reaction for photosynthesis. We left out the light energy, but it would be a reactant here. And we're making glucose and oxygen, and we want to know what mass in grams of glucose, so this C6H12O6, can we do if we have 3 moles of water over here. So our given, or our known, is the 3 moles of water, because that's what they told us in the problem, and our unknown is how many grams of glucose could we make. So again, we're just going from the moles of water over to the moles of glucose. And what you can see here is we're going to start in moles of water, do a conversion to get to moles of glucose, and then do another conversion to get to the grams of glucose over here. And what the problem actually looks like is down here. So I'm writing out my known. I have my 3 moles of water right here. And then I made a conversion factor, and the conversion factor is my mole ratio. So I looked at my reaction, and I have 1 mole of glucose, and that goes on top because that's what I want, divided by my 6 moles of water, which goes on the bottom here. and that's what I'm trying to cancel out mathematically. And then the other thing I need my grams of glucose. So I'm looking at my molar mass, and 1 mole of glucose on the periodic table happens to weigh exactly 180 grams. So make sure that everything cancels. Moles of water canceled, moles of glucose canceled. I'm going to end up in grams of glucose. Do the math, and you should get exactly 90.0 grams of glucose, and we have 3 sig figs because of the given measurement of the 3 moles of water. So what I would suggest you doing is, then there's another problem where, what if I was crazy and I let you burn like tons of magnesium, like 50 grams of magnesium? So it'd be really pretty but kind of dangerous. So what you should try and do is do it and then see what you get, and then you can always come in and check it. But this is just like this last type of problem where you're going from moles to mass. So next one we're going to do is just the opposite of this one, and we'll come back to the stoichiometry in a second here. Now we're going mass to moles, so it's just the opposite of last type. But now when we're starting here, we're starting with the mass of our known product. So what we need to do right away is we need to get to moles. So we look up our molar mass from the periodic table, and that allows us to convert to moles. And then we do our mole ratio to get to the unknown, and then in this type of problem we stop, which kind of seems abrupt, but that's all they want, so then we just stop there. It's still going to be a 2 conversion factor, but it's going to be a slightly different order, and we're getting the molar mass of our given as opposed to our unknown for that one. All right, so what we're doing here is, this is just a reaction that happens a lot when you're making nitric acid. So you have ammonia, you're reacting with oxygen, you're making nitrogen monoxide and water. And here's the balanced equation. It's kind of a nastier balance, so there you have that. And if you read this, it says the reaction is run using 824 grams of ammonia and excess oxygen. Anytime a problem says excess oxygen, what they're trying to tell you is there's extra of it. What it means is it's not going to affect your math because you have more than enough of it. So what it means is you can kind of just ignore it, which is nice. And we're going to do part A. And like I said, I would suggest you doing part B to make sure you're okay with it. But we want to know how many moles of nitrogen monoxide are formed. So again, our given is 824 grams of ammonia. Our unknown is the moles of NO, and that's what they're asking us. So we're going to have a 2-step problem. We're going to start in grams, go to moles, and then we're going to go from moles of ammonia to moles of nitrogen monoxide. So if you look back at stoichiometryville, first thing we need to do is get the molar mass from the known thing or the given, and then we're going to do our mole ratio. So I have my 824 grams of ammonia. First thing I did is I looked up the molar mass on the periodic table. Because I'm giving grams, I need to have my grams on the bottom to cancel it out. So I just inverted my molar mass, and I'm allowed to do that. That gives me moles of ammonia. So you can see here that's our first step. Second thing I need is I need a mole ratio. So I go to my chemical reaction, and I have 4 moles of NH3 for every 4 moles of NO. So I have my mole ratio there. If you want to, you could write 1 to 1. It's just I don't simplify because I don't want to mess myself up, but you are welcome to if you want to. Make sure everything cancels, and it does. And then do your math, and you should get 48.5 moles of nitrogen monoxide. All right, so we have 2 more here. The next one is kind of just putting the other 2 together. This is the most common one because this is the one you typically do in lab. And what you're doing is you're going from mass to mass. So you're just going the whole way through. When you look at stoichiometryville, it's just going the whole way over. And again, we focus on mass to mass because it's the most common, but you can do this with particles. You can do this with gases as well. So remember, at STP, that just means at standard temperature and pressure. And you just can go from there.